All right, another week. Time for your questions. My answers. That's a Stellar's J. Wherever you are on my channel, you done? Go ahead. Question pops into your brain, just type it in. I will gather a bunch of them up and I'll answer them here. I got another special guest answerer, so please stick around to the end. I think you'll really enjoy it. All right, let's get on with the questions. JanJorre Laurens. Hey Fraser, just had a random question and I thought of you. Recently, astrophysics discovered that a lot of the really heavy elements are created in neutron star collisions. Could a potential solution to the Fermi paradox be that there haven't been enough of these collisions for earlier civilizations to have been able to discover or invent space technologies? I mean, I guess this is like one possible answer to the Fermi paradox, right? This idea, where are all the aliens? But the thing is that the universe is really old, right? 13.8 billion years. The amount of time, and the sun has only been here for about 4.5 billion years. So there's been just billions and billions of years that could have happened. And these neutron stars have been colliding, again, for billions and billions of years. So these heavier elements have been there. And so it doesn't seem like we're right at the very cutting edge of the heaviest elements that could be available to achieve spaceflight. Feels like there would have been, even within the few billion years, opportunities that you could have had heavier elements seeded into stellar nebula, and that would have created potentially intelligent civilizations, and they would have gone on to colonize the Milky Way. So it just doesn't feel like any of those reasons, right? Like this one comes up quite a lot. Like why, what if it's sort of like a race and we just all happen to be like right at the very cutting edge? And that's just not what you would expect. You would just expect different civilizations who have come and gone over the billions of years, over the history of the universe and the Milky Way, which is essentially as old as the universe. And it seems really unlikely that we're just like the very first. And yet, of course, where are they, right? So Fermi paradox just continues to puzzle. Stephen Utter. The lava. You say it as if you're about to say llama. I've mentioned this in the past that, I'm Canadian. I know we sort of sound like Americans, but we have a few distinct differences. For example, we say A all the time, just all the time. And it's pronounced a boot. So just keep that in mind. And of course, if you want to use the last letter of the alphabet, it's Z, right? Which doesn't rhyme with Now I Know My ABCs, but that's just what we learned. Literally, we learned to sing the ABC song and end in Z. So there you go. Yeah, I say llama, I say pasta, I say lava, and that's apparently it's a West Coast Canadian thing. Anyway, there you go. Sorry. I appreciate like literally 5 or 6 of you are trying to teach me how to speak American, and I really appreciate that. Tanner Ali. I think it will be awesome if you make a video or two about the 2018 NASA Innovative Advanced Concepts Awards. They're always very interesting and you manage to convey complex information very well. Keep up the good work and thanks. You're talking about the Nyack Awards, the NASA Innovative Advanced Concepts, and I'm a huge fan. I would say it's like Christmas every year when the new Nyack Awards are released. And this one is big. There are like a dozen of the Phase 1 prizes that were awarded and like another dozen of the Phase 2. So there are like 25 plus really cool out of the box thinking. Robotic bees that would be sent to Mars, various ways of beaming for propulsion, a hopper that would fly on Titan. And I will definitely be covering as many of these ideas as I can sort of get around to. Very few, like when I did the Europa mission, that actually was a Nyack Award that I was talking about, and of course it never happened or hasn't happened yet. So very few of these missions actually end up turning into a mission that flies, but still, I just enjoy the ideas in them so much, and I will definitely be covering them, and I'll mention, when you hear me say Nyack or Innovative Advanced Concepts, that is this award, and I highly recommend you go and look at the list, but I will try to cover as many of them as I can. Predrag Bubalo. If there are open vents and geysers of water breaking through the surface on Europa, why the need to drill through kilometers of ice? Couldn't the probes gain access to the water through these vents and geysers? Yeah, this is based on the, again, on the Europa, what's under the ice. And I mentioned in the video sort of the complicated way that you would try to drill down to get through all that ice and try to examine what's underneath it all. And the reality is, you're exactly right. On Enceladus, we know that there are these geysers. There's got to be water that's very close to the surface, and it's making its way out into space. And one of the things that the Europa Clipper is going to be doing, and this mission is approved, it's getting built, and it will be launching to Europa, is it's going to have this ground penetrating radar on board that will be able to map out the ice and sort of the densities and where there could be open pockets. If there's water, what is the depth of the oceans on Europa? And so we're going to find out, and there could very well be that there are chambers of water, there are, you know, geysers and vents and places which will be a lot easier to explore, and maybe that's what they'll do first. But I think there's something really important about getting through the ice itself and actually getting to the ocean and being able to explore both the ocean, and even in this mission they talked about going right down to the seabed and being able to sort of sample that and see what kind of life is down there. So I think both are important. Let's start by trying to sample as much of the water as we can that's close to the surface, and then as we get more confident about what's going on there, let's go deeper and deeper, and even under the ice itself. Mighty 13. Don't know how NASA will respond if an innovative project such as the BFR really comes to life. They will hand over their money and they will buy flights on the BFR. I mentioned this in a previous video, that NASA's being so, people saying like, oh, NASA's being so challenged by what SpaceX is doing. NASA is SpaceX's biggest customer. We just saw the launch of the 14th resupply mission to the International Space Station using a SpaceX Dragon capsule on a Falcon 9, right? NASA gave SpaceX money when nobody else would. They helped to really kind of let that company get going and build itself up to scale. Now, they've mentioned that they don't want to buy flights on the Falcon Heavy. We'll see if that actually turns out to be the case. But if the BFR comes to be, and you're looking at $7 million of fuel to refuel the BFR, the thing can fly to space, totally reusable, then it's going to bring the launch cost, 250 tons to orbit. It's going to bring the launch cost down so cheap that there's really no other option, and NASA will be glad. Remember that every mission that NASA can do to fly on these less expensive orbital rockets is the more science payloads they can do. If they fly on something like the BFR, they get to double, triple the number of missions that they have to make because they don't have to pay for an expensive launch cost. So again, NASA can't wait to be able to buy flights, and I'm sure they can't wait to be out of the rocket launching business. Jeffrey Gould. Hello, Fraser. Since some white dwarfs and neutron stars have been found to spin at incredible speeds, I was wondering if they may come close to flinging anything off their equator or even canceling a significant fraction of their own tremendous gravity at the surface. Is this even possible within our laws of physics? Neutron stars, there's kind of no limit to what they can, well, they can spin to the limits predicted by relativity and can spin thousands of times a second. But white dwarfs, these are the remnants of stars like our own, when they can rotate very quickly, and you can have special conditions where they end up rotating so fast that they can tear themselves apart. And there's been a couple of examples where astronomers have detected, and there's one for sure, where they have detected a white dwarf kind of spinning so quickly that it tore itself apart. And I'll try to put a link into the show notes so you can see that. So it can happen, and it just shows you the immense speeds and forces that are going on to bring these objects together. Brian Blatz. Fraser, why the green screen nature background and piped in nature noises? Would an astronomical background be more appropriate? Yeah, we just shoot outside. This is my backyard right now. These are lovely cedar trees here on the West Coast. When my wife moved here from Texas, she noted that everything looks like Christmas trees, and we just call them trees. And birds, yeah, we're in the springtime now, and I'm standing right beside, I just saw two juncos fight. We're standing right beside where we've got a bird feeder out on our deck, and the birds just go crazy. And yeah, so we don't have a green screen. Our green screen has one setting, which is outside on the west coast of Vancouver Island. Or at Forest of Endor, isn't that what I said in the last video? Guybrush Threepwood. Hi Fraser, how big was the observable universe before the Big Bang? We don't know. We don't know what happened before the Big Bang. All we know is that there was the Big Bang. And I think, when you think of the Big Bang, you think of this explosion, that you had nothing, and then you had an explosion, and then you had something. But that is not the right way to really look at it. Think of it like this. You have a rubber band, and you start with the rubber band, and it's one size, and then you stretch the rubber band, and now it's a bigger size, or less dense. We know that the universe has the density that it has today, and we can see all of these objects flying away from each other in all directions. And if you run the clock backwards, you bring all those things together and closer together, and eventually what used to be things that were light years, billions of light years apart, were incredibly close. We don't know how close, but we don't know what came before that. It could very well be that the universe had been around for an infinite amount of time at this more dense size, and then it went through this process of inflation and expanded, and then we had the Big Bang, or the expansion that we see today. We don't know how long it was in the state, whatever it was, before the Big Bang. And it's entirely possible that we'll never know. It's just that we have no way to be able to probe before what came before this rapid expansion. All we know is from the rapid expansion onward. Leslie B. Hi Fraser, I like your channel a lot. I have a question. What will happen to Jupiter when it stops being active? Will it lose its atmosphere? Will there be a surface? What will it look like? Jupiter is a gas giant. So Jupiter is made of hydrogen and helium with some other elements, heavier elements, like several times the mass of the Earth in rock and things like that. But mainly, like the vast majority of it is hydrogen and helium. And these are the same kinds of gases that are in the sun. So Jupiter, if just left to its own devices, would just sort of remain in its current form for a very long time. And it would be slowly cooling down to the background temperature of the universe. It's not going to ever clear away its hydrogen and helium. It's just going to remain in this form, but eventually just be a much colder version of what it is today. Locutus. Do you ever feel that you live at both the best and worst time in human history in the terms of space exploration and cosmology? I feel like we've picked a lot of the low-hanging fruit, and that despite there still being much more amazement to come, we are now looking at missions, probes, telescopes, and physics experiments that require more and more funding and longer planning. At the speed of progress of other technologies like the advancements in AI, material science, biology, etc., I can only imagine where we will be at the end of my life. But by comparison, many missions and new promising probes, telescopes, etc. take 20 to 30 years to come to fruition. This can seem disheartening at times. Oh, it's not disheartening, it's still very exciting. Like right now, when I'm recording this, or by the time you see this, hopefully the test mission will have launched. The NASA's solar probe is about to launch. There's the Hayabusa 2 mission is about to rendezvous with Jupiter. With the Hayabusa probe is about to rendezvous with an asteroid. You've got the Mars InSight lander is about to take off and give us an idea if there are active volcanism on the surface of Mars. There's other various telescopes and missions that are in the works. There's going to be lots more stuff. Again, I've been doing this for 20 years now, and I find that my days are always packed. In fact, they feel more packed now with all of the missions and discoveries and things that are going on than they've ever been. The BFR is going to be doing its test flights next year. The SLS is going to be coming after that. James Webb someday is going to launch. So the timelines do extend for sure, but they've always been long, right? The Hubble Space Telescope, the first developments for that, they started working on that in the 1970s, and it didn't launch until the 90s, and it still had to be fixed. So this is pretty normal to have these big, long timelines. You've just never noticed before. So don't worry about it. Just get excited about the things that are about to release their discoveries now, and don't worry, there's more always coming all the time. Ferus Gratia. Hey Fraser, thanks to all the work you and YouTubers like you do, I feel like I have a much better grasp of space and to some extent cosmology. That said, it's been a bit since I've had my mind blown by some new fact. I think I'm ready to delve into materials that would be hard to cover on YouTube, but I don't think I'm ready for hardcore scientific journals. Do you know of any good middle ground resources? Thanks. Yeah, I can think of a bunch of things. The first thing is if you watch a lot of the videos, I say, now here's a playlist. When I link up that playlist, I'm generally linking stuff that is more in-depth, deeper, often hour-long lectures on what I just talked about from the original researchers. So for the episode on TESS and Kepler, I know I linked to a bunch of very long, very extensive talks. There's stuff by even here on YouTube, there's some pretty great talks from like the Perimeter Institute. Things like that are very, very complicated. If you want to read things, I actually think you are ready to handle some of the scientific journals. Go to AstroPH, we call it Archive, and that is a place where all the astrophysicists and space scientists, they post their journal articles. And some of them I'm sure are going to go right over your head, but others I'll bet you are within your reach. And I often will go in there and look for interesting stories to cover, or if I'm looking to expand upon some of the things that I'm talking about here, I'll look through some of those journal articles. Yeah, if you want a sort of a middle stage between journal articles and what's written for kind of the general public, I really like AstroBytes, which is sort of graduate students are taking journal articles and writing articles about them. And it's a lot of interesting news that you'll never have heard, but it's really well covered. So I highly recommend those. But if you want more resources, let me know. I will continue to point you in the right direction. Alpha 581. Love your videos as always. I have an interesting question for you. Assuming that the universe is infinite and you travel far enough, will you eventually meet an exact copy of Earth and humans by random coincidence? Yeah, we talked about this in a video called Is the Universe Finite or Infinite? And I'll give you sort of the short version of this, right? Let's imagine that the universe is infinite. Then you can, and there are a sort of finite number of ways that particles in the universe can be. So if you take like a cubic meter of space, you're going to have a set of sort of finite number of ways that all of the particles can be in that cubic meter of space, right? And it's like 10 to the power of 80 or some huge number. But for the observable universe, you're never going to see a copy of that cubic meter. But if you go billions, trillions, quadrillions of light years away, you will eventually have essentially a repeat of a cubic meter of space. And if you go even further and even further, you're eventually going to have larger repeats. And eventually everything will be repeated. And in fact, because it's infinite, it'll be repeated an infinite number of times. And so you can imagine eventually there is a repeat of us here on a planet that's like the Earth, and a person standing in front of a camera. That potentially is going to happen an infinite number of times, and every other version of that as well. Norman, 1951 Norman. What percentage of exoplanetary systems align with Earth in such a way that their orbital planes pass across the star's disk as seen from Earth? I can't imagine that it would be very high. Great show. Great question, but I'm not going to answer it. I'm going to give this over to a special guest answer, Dr. David Kipping, who is a professor and an exoplanetary researcher at Columbia University. And he does his own YouTube channel here called Cool Worlds. You totally got to check it out. All right, here's David.
That's a great question, Norman, but not a straightforward one to answer. The percentage or fraction of planets which transit in front of their star equals the sum, the total, of all of the planet's individual transit probabilities. And that probability depends on two factors. So let's imagine that this disk is my star and this espresso pod is my planet. The chance that someone off to the side over there will see these two objects line up and thus cause a transit will be higher if I make this disk much, much bigger. So the transit probability depends on the size of the star, and that's different for every star system you look at. Now, hopefully you can also see that if I have my star and my planet very close together, maybe something like a hot Jupiter system, the range of angles which allow for a transit to be seen is pretty broad. Whereas if I separate them apart, maybe something more like Pluto around the sun, the range of angles is now much narrower, so the transit probability is less. So overall, the transit probability equals the star's radius divided by the separation to the planet. For the Earth-Sun system, that's something like 0.5%, whereas if I'm talking about a hot Jupiter, it could be as high as 10% or even higher than that. So the true fraction of planets which transit their star depends on the distribution of the planet properties, and that's something that astronomers like us here at Columbia University at the Cool Worlds Lab are trying to actively uncover.
Thanks, David. Great answer. As always, you should totally check out his channel, Cool Worlds. I'll put it in the playlist at the end of this. I'll put it in the show notes, and you can go and subscribe. It is a great channel. If you really want to get into the details of extrasolar planets, check it out. All right, that's it. Those are all our questions. As always, wherever you are on my channel, if a question pops into your brain, type it down. I will gather them all up, and I'll answer them here. I'll see you next week.